I would want to welcome you back to my channel. This time we're going to be working on the Further Pure Mathematics Paper 1 for May-June 2020. So this is 9231 Paper 11. So let's get started. Question number 1. Let A be a positive constant. So on A, sketch the curve with the equation y is equal to ax over x plus 7. So here we want to make a sketch of a rational graph. And before making a sketch, it's important for us to determine, first of all, the vertical asymptote. And for the vertical asymptote, we know that we simply have to equate the denominator, which is x plus 7, to 0. So x comes out as minus 7. So this is the equation of the vertical asymptote. Then for the horizontal asymptote, you simply have to look at the degree of the numerator and that of the denominator. And we can see that the degree of the numerator is the same as the degree of the denominator. So here you just divide the coefficients. So that's a over 1. So it's y is equal to a. And then you also have to consider the intercepts. And for the intercept, we're going to say what is y when x is equal to 0. Now, if you substitute 0 into this equation, you're going to get that y also comes out as 0. Alright, so now we have the vertical asymptote, the horizontal asymptote, and the intercept, which is the point 0, 0. That's the origin. So we can start making a sketch. This is the vertical axis, and we have the horizontal axis here. So y and x. This is the origin, and we have the vertical asymptote as x is equal to minus 7. So here it is. So this is minus 7. And the horizontal asymptote is y is equal to a. So here it is. Now when sketching a rational graph, you also need to study the behavior of the graph around the asymptotes. So starting with the vertical asymptote, if we take a value that is slightly greater than minus 7, for example, x is equal to minus 6.9, substituting that into the equation of y, then you will find that we get a y value of minus 69a, which means for values that are slightly greater than minus 7, the graph has a very low value of minus 69. So the graph is going to be coming from down below here. And also, for values of x that are slightly less than minus 7, take for example minus 7.1, substituting that into the equation of y, we will get a y value of 79a, which is a big number. So we know that the graph on the left side of the vertical asymptote is going to be coming from around here. We also need to study the behavior of the graph about the horizontal asymptote. So here we can consider a very large x value. For example, x is equal to 1000. If we substitute that into the equation of y, we will get a value that is slightly below a, like 0.99a, which means the graph will come from down below. And also we will consider a very small x value. For example, x is equal to minus 1000. And if we do so, we get a y value of 1.01a, which is slightly above a. So we now have an idea of how our graph is going to be like. So we can now make a sketch. So here it will just come out like this. And here it will come out like this. So this is the graph right here. Let's go on to part B. Part B. Sketch the curve with the equation y is equal to mod ax over x plus 7 and find the set of values of x for which mod ax over x plus 7 is greater than a over 2. So here we want to sketch the modulus graph, the modulus of the graph y. So we're going to reflect the part of this graph that is below the x-axis. So I'll just take part of this graph that is above, and I'll place it here. So this is the part of the graph that is above the x-axis. So I've left out the one that is below. Okay, so this is still the x-axis. This is still the point -7. So what we're going to do here is we're going to reflect the part of the graph that is below the x-axis above the x-axis. So it should come out to be somehow like this. So that's what we want to do. So let's do it here, which means our modulus graph will come out like this. We have the origin around here. So that's it for the graph. Then the other part of the question goes, find the set of values of which mod of ax over x plus 7 is greater than a over 2. So here we're going to consider the graph of y is equal to a over 2. Now a over 2 is half of a, which means that we can have the line or the graph come out like this. I'll use a different color for it. So I'll say this is y is equal to a over 2. So we would want to find the values for which the graph, the modulus graph, is greater or above the graph of y is equal to a over 2. So let's now consider the points of intersection of the two graphs. So the two graphs are intersecting at 2 points. So let's start with this point of intersection. This is where the graph of ax over x plus 7 is intersecting with the graph of the line y is equal to a over 2. So this is the first point of intersection. And then for the second point of intersection, which is this point here, this is where the portion of the graph, which is the reflected portion, which I can denote minus of ax over x plus 7, is intersecting the line y is equal to a over 2. So here now I can solve for x. Alright, so by cross multiplying and also considering that a appears on both sides, so I'll divide both sides by a, I will get 2x is equal to x plus 7. And if I solve for x here, I will get x coming out as equal to 7. So this point here corresponds to 7. And then for the other point of intersection here, which is where the reflected portion of the graph, which has the equation minus of ax over x plus 7, is intersecting the line y is equal to a over 2. So I can also solve for x through cross multiplying and dividing both sides by a. I will get minus 2x is equal to x plus 7. And when I solve for x here, I'm going to get minus 7 over 3. So this point here is minus 7 over 3. So we now have the two critical points, and now we can solve the inequality. So remember, we want to solve this inequality, that the graph of mod ax over x plus 7 is greater than a over 2. So looking at it graphically, you can see that the graph of modulus is above the graph of y is equal to a over 2 for values of x that are greater than 7. So as we go beyond 7, the graph of modulus is greater or above the graph of y is equal to a over 2. And if we go back to the other critical point, which is the point where x is minus 7 over 3, you can also see that as we move from minus 7 over 3 moving to the left, the graph of modulus is also above that of y is equal to a over 2. But this is all the way up to minus 7, which is an asymptote. So we now have a set of values from minus 7 to minus 7 over 3. And then for the last part of the graph, which is less than minus 7, to the left of minus 7, the graph of modulus is also greater or above that of y is equal to a over 2, which means that also for values of x that are less than minus 7, the graph of modulus is greater than that of a over 2. So we now come out with these three inequalities, and that's the answer. Question number 2. The cubic equation 6x cubed plus px squared minus 3x minus 5 equal to 0, where p is a constant, has roots alpha, beta, and gamma. So on A, find a cubic equation whose roots are alpha squared, beta squared, and gamma squared. So what we will do with this one is, we'll say let y be equal to alpha squared, which translates to alpha being y to the power of a half. Now, since alpha is a root of this cubic polynomial equation, I can substitute alpha into this, where alpha, we're using the substitution of y to the power of a half. So we'll now be having 6 of y to the power of a half cubed plus p of y to the power of a half squared minus 3 of y to the power of a half minus 5 is equal to 0. So let's simplify this. Here I'll be having 6y to the power of 3 over 2. And here I'll be having p, and here I'll multiply the powers, and half times 2 we get 1, so that's py, and that's minus 3y to the power of a half, that's minus 5 equal to 0. Now I have fractional powers here, so what I'll do is I'll take py and minus 5 to the right side, which means I'll be having 5 minus py here. And on the left side, I'm left with 6y to the 3 over 2 minus 3y to the power of a half. Now 6y to the power of 3 over 2, I can write it as 6y of y to the power of a half. And that's minus 3y to the power of a half. And I've done this so that I can factor out y to the power of a half, which means I'll be having inside the bracket 6y minus 3, and that's all equal to 5 minus py. So from here I can square both sides, and if I do this, then it means on the left side, squaring y to the power of a half, I get y, and squaring 6y minus 3, I get 36y that 36y squared rather. So 36y squared minus 36y plus 9, and it's equal to, here I'll be having squaring 25 minus 10 py plus p squared y squared. Further simplifying, we have 36y cubed minus 36y squared plus 9y is equal to 25 minus 10 py plus p squared y squared. Let's take everything to one side in grouping. So we'll be having 36y cubed minus 36y squared, and from the right side I take the p squared y squared, so it becomes minus p squared y squared. I take the 9y and minus 10 py coming to the left side will now become plus 10 py, and that's minus 25, and it's all equal to 0. Let's see what we'll get here. So I can factor out y squared to get inside the bracket 36 plus p squared, and that's of y squared, and here I can factor out y, so I have 9 plus 10p of y, that's minus 25, it's all equal to 0. So what I now have here is a form of a cubic equation which has roots alpha squared, beta squared, and gamma squared. So this is the answer for part A. Let's scroll down to part B. It is given that alpha squared plus beta squared plus gamma squared is equal to 2 of alpha plus beta plus gamma. So on part 1, find the value of P. Now let's start with alpha squared plus beta squared plus gamma squared. This is the sum of roots of the cubic equation that we got on A. So in order for us to get the sum of roots for this cubic equation, this will simply be equal to minus of the coefficient of y squared, which is 36 plus p squared, over the coefficient of y cubed, which is 36. So that's the sum of roots here. And for the right side, we've got 2 of alpha plus beta plus gamma. And here we're talking about the sum of roots of the first cubic equation. It's minus of the coefficient of x squared, that's minus p, over the coefficient of x cubed, which is 6. So it's minus p over 6 for sum of roots. So that's minus p over 6. So let's simplify this. So I know that if I divide 2 into 6, I get 3. And through cross multiplication, I'll be having 3 of 36 plus p squared is equal to, and here I'll be having minus of 36p. Then if I divide both sides by 3, I will be left with 36 plus p squared is equal to minus 12p. And putting everything to the left side, I'll be having p squared plus 12p plus 36 is equal to 0. So I can factorize. And here I'll be having p plus 6 and p plus 6. Which therefore means that p plus 6 is equal to 0 and p comes out as minus 6. So this here is the answer. Let's go on to the next part of the question, B part 2. Find the equation of alpha cubed plus beta cubed plus gamma cubed. Now, for us to find this, let us consider the original cubic equation. Now, the original cubic equation is this one. So let's put it here. Now, for this cubic equation, we had found the value of P, and the value of P on part B, we got it to be minus 6. So it means the equation is 6x cubed, that's minus 6x squared, minus 3x minus 5 is equal to 0. But here I'll write it with 6x cubed subject as 6x cubed is equal to 6x squared plus 3x plus 5. And since alpha is a root of this equation, so we can say 6 alpha cubed is equal to 6 alpha squared plus 3 alpha plus 5. Beta is also a root of this equation. So 6 beta cubed is equal to 6 of beta squared plus 3 beta plus 5. And lastly, we know that gamma is also a root of this. So 6 gamma cubed is equal to 6 gamma squared plus 3 gamma plus 5. So we now have 3 equations. So that's 1, that's 2, and that's 3. So if we add the 3 equations, 1 plus 2 plus 3, what we're going to get is, here on the left side we'll be having 6 of alpha cubed plus beta cubed plus gamma cubed. And on the right side we'll be having 6 of alpha squared plus beta squared plus gamma squared. and that's plus 3 of alpha plus beta plus gamma, and that's plus 5 plus 5 plus 5, that's 15. Now alpha squared plus beta squared plus gamma squared, we have it from part B, where we had alpha squared plus beta squared plus gamma squared as 36 plus p squared over 36. So let's have that. So this is 36 plus p squared. Remember, we got p as minus 6. So minus 6 squared is 36 over 36. And that's plus 3 of alpha plus beta plus gamma is sum of roots. And on part B, alpha plus beta plus gamma, we'd say that's minus p over 6. So let's just use that, minus p over 6. So that's, since p is minus 6, it will just come out as 6 over 6, which is 1, but let's just write it like this, and it's plus 15. Okay, all right, so this is 36 plus 36 divided by 36, that's 2. 6 times 2 is 12, and that's plus 3 times 1 is 3, and 15 here. It's all equal to 6 of alpha cube plus beta cube plus gamma cube, which means that simplifying, we get 30 here, which therefore means that alpha cube plus beta cube plus gamma cube will be dividing both sides by 6. We get 30 divided by 6. So we can say alpha cube plus beta cube plus gamma cube is equal to 5. And that's the answer right here. Question number 3. The curve C has equation y is equal to x squared over 2x plus 1. So on A, find the equations of the asymptotes of C. Okay, so here let's start with the vertical asymptote. And for the vertical asymptote, we're going to say 2x plus 1 is equal to 0. Therefore, x comes out as minus a half. And then for the other asymptote, if you look at this equation, you can see that the degree of the numerator is 1 greater than the degree of the denominator. And what that means is that we're going to be having an oblique asymptote here. So what I'll do is for the oblique asymptote, I'm going to divide 2x plus 1 into x squared. So let's do that. So I'll write here x squared plus 0x plus 0 and divide 2x into x squared. I get half of x, and multiply half of x times 2x plus 1. So that gives me x squared plus a half of x. Then I subtract x squared minus x squared is 0, and 0 minus a half x, I get half minus half of x. Then 2x into minus a half of x, I get minus a quarter, and minus a quarter times 2x plus 1, here I have to bring down 0, I get minus a half of x, and minus a quarter times 1, I get minus a quarter. And here finally the remainder is going to come out as I get a quarter here. So basically the quotient here forms the equation of the asymptote. Therefore the equation of the oblique asymptote is y is equal to half x minus a quarter. So that's what we get for the oblique asymptote. Let's go on to part B. Find the coordinates of the stationary points on C. Okay, so we have right here the equation y is equal to x squared over 2x plus 1. So let's find dy by dx. So we use the quotient rule here. So this will be equal to 2x plus 1 times the derivative of x squared minus x squared, and we differentiate 2x plus 1, and then it's all over 2x plus 1 squared. So what we get from this is, differentiating x squared, we get 2x, so we have 2x of 2x plus 1, and differentiating 2x plus 1, we get 2, so it's minus 2x squared, and it's all divided by 2x plus 1 squared. Now simplifying the numerator, we have 2x times 2x, that's 4x squared, and minus 2x squared, it gives us 2x squared here. And then 2x plus 1, this will give us plus 2x, and it's all over 2x plus 1 squared. Now I will equate this thing to 0. So this is equal to 0 at stationary point. Okay, and equating this to 0, I multiply both sides by the denominator. So I'm left with 2x squared plus 2x being equal to 0. And I factor out 2x here, so I'll get x plus 1 inside the bracket, which means that I can equate 2x to 0 to get x coming out as 0, and x plus 1 to 0 to get also x coming out as minus 1. Now if x is 0, in the original equation, substituting 0 for x, I get y coming out as 0. And when x is minus 1, substituting minus 1 into this equation, I get y coming out as minus 1. So therefore, the coordinates of the stationary points will come out as 0, 0, and minus 1 and minus 1. So this is the answer right here. Let's move on to part C. So they say sketch C. Okay, so let's have the two axes. So we have y and we have x here and the origin. Let's put in the asymptotes. The asymptotes, we have x is equal to minus a half as the vertical asymptote, and the oblique asymptote of y is equal to half of x minus a quarter. So let's start with the vertical asymptote. So the vertical asymptote is x is equal to minus of a half. So we have minus a half here. And we also have the oblique asymptote. Y is equal to half x minus a quarter. So it goes like this. So this is the oblique asymptote. Crosses the y-axis at minus a quarter. And the x-axis at half. So we can now make a sketch. We also have to consider the turning points. So that's at 0, 0 and minus 1, minus 1. So it'll come out like this. With the minimum point at 0, 0. And the other part of the graph will be like this. So we now have the sketch of C, and that's how we do it. Question number 4. Part A. By first expressing 1 over r squared minus 1 in partial fractions, show that the summation from r is equal to 2 up to n of the form 1 over r squared minus 1 is equal to 3/4 minus an plus b over 2n of n plus 1, where a and b are integers to be found. Okay, so for this one here, what we're going to do first is we're going to express 1 over r squared minus 1 in partial fractions, and this is going to give us a over r plus 1 plus b over r minus 1. So we can form an identity of 1 being identical to a of r minus 1 plus b of r plus 1. So here we can say, using the cover-up method, if r is equal to 1, It therefore means that 1 will be equal to, this will be covered up, becomes 0. So 1 plus 1 is 2. So we have 2b here. And this translates to b coming out as a half. And we can also say if r is equal to minus 1, if r is equal to minus 1, it means that this will become a minus 2a. So we'll be having here 1 being equal to minus 2a, while this part gets covered up because minus 1 plus 1 is 0. So this whole thing becomes 0. So this will translate to a coming out as minus a half. So now that we have the values of a and b, we can therefore express 1 over r squared minus 1 as, here factoring out the half, I'll take the half out. And then I will have inside the bracket, since b is the one that's coming out positive, I'll have 1 over r minus 1 minus 1 over r plus 1. So this is what we will have eventually if we express this in partial fractions. Alright, now we want to work out the summation. Now we have the summation from r is equal to 2 up to n of the form 1 over r squared minus 1 being equal to the summation from r is equal to 2 up to n of this expression here, which is in partial fractions. So that's half of 1 over r minus 1 minus 1 over r plus 1, like this. Now I prefer to work out summations going down. So here I'll say 4 and I'll leave out the half for now. So I'll say 4, the summation from r is equal to 2 up to n of 1 over r minus 1 minus 1 over r plus 1. This will give us the first term, which is when r is equal to 2, coming out to be 1 over 1 minus 1 over 3 if we substitute 2 into this. And when r is equal to 3, which gives us the next term, that will be 1 over 2 minus 1 over 4. And when r is equal to 4, then we'll be having it coming out as 1 over 3 minus 1 over 5. And when r is equal to 5, I think we'll end it here, we will get 1 over 4 minus 1 over 6. So it will continue going all the way down until we reach the second from last term, which will be when r is equal to n minus 1. Now when r is equal to n minus 1, if we substitute this into this expression here, we'll be having 1 over n minus 1 minus 1, which is 1 over n minus 2, and that's minus 1 over n minus 1 plus 1, which is just 1 over n. And the last term of the series comes out when r is equal to n, which is 1 over n minus 1 minus 1 over n plus 1. Now these are some of the terms in this series. So we have the first 4 terms and the last 2 terms. And if you can study the pattern, you can notice that if we are going to add the terms, then a term like minus a third gets added to a third so that they get eliminated. And then a term like minus a quarter, if we skip one term, we find a quarter here to add to it, and therefore we eliminate them. So I think you can notice that all the terms that are inside will always find another term to add to them and therefore eliminate. So this will happen to minus a fifth and minus a sixth. This will also happen to minus 1 over 2, which will find a term somewhere along the way to add to and get them eliminated. 1 over n minus 1 will have a term somewhere around n is equal to minus 2 to eliminate it. So eventually we are left out with 1 over 1, a half, minus 1 over n, and minus 1 over n plus 1. So we can therefore say that the summation from r is equal to 2 up to n of, I'll now put in the half, so that's of a half of 1 over r minus 1 minus 1 over r plus 1 is going to come out as a half of, and I'll take 1 over 1 here, which is 1, and the half, which is plus a half, and the minus 1 over n, so minus 1 over n, and minus 1 over n plus 1 right here. And we can simplify this now to give us a half of 1 plus a half, that's 3 over 2. And for this one, I will just have a common denominator of n plus 1. So here we will get n plus 1, and that's plus n. And we can simplify this again to get a half of 3 over 2 minus n plus n here, that's 2n plus 1 over n of n plus 1. And finally, half times 3 over 2, that's 3/4, minus half times this algebraic fraction here, we get 2n plus 1 over 2n of n plus 1. And what we have formed here is what they wanted us to get. Let's scroll down to part B. On part B, the question goes, deduce the value of the summation from r is equal to 2 to infinity of 1 over r squared minus 1. Now you see how we had worked out the summation of this thing from r is equal to 2 up to n, and we had gotten for ourselves 3/4 minus 2n plus 1 over 2n of n plus 1. And here they want us to find the summation from 2 all the way up to infinity. So this is the same as we're looking for, the limit as n approaches infinity of this whole thing here. So this will come out as, for the constants, I'll just have 3/4 here, minus, and here for the limit as n approaches infinity, you can see that the denominator will increase at a much faster rate than the numerator as n increases, making this whole algebraic fraction here approach 0. So eventually we will get 3/4 as our answer. Let's move on to part C. So on C it says, find the limit as n approaches infinity of the summation from r is equal to n plus 1 up to 2n of the form n over r squared minus 1. Now from part A, we had worked out and gotten this for the summation from r is equal to 2 up to n of the form 1 over r squared minus 1. So we can use this and say the summation from r is equal to n plus 1 up to 2n of the form n over r squared minus 1 is the same as the summation from the lower limit. We'll use 2, so r is equal to 2 up to 2n of the form n over r squared minus 1 minus the summation from r is equal to 2 to n of the form n over r squared minus 1. So let's simplify this for now. So here we are saying that the summation from r is equal to 2 up to 2n of the form n over r squared minus 1 means that we have n factored out, and here in this expression for the summation, in place of n we'll have 2n, so it will now come out as 3/4 minus, and here that will be 4n plus 1 over, and again putting 2n for n, we'll be having 4n here and 2n here plus 1. So this is what we have for the first one. And that's minus, and the summation from r is equal to 2 up to n of the form n over r squared minus 1 means we only have n faded out, but everything remains the same. So that's 3/4 minus 2n plus 1 over 2n of n plus 1. So this is what we have. So let's simplify this a little bit more. So multiplying by n, we have 3/4 of n minus, here we'll be having 4n squared plus n over, and at the bottom here, what I'm going to do is I'll expand the brackets. So we'll be having 8n squared plus 4n, and that's minus, here we'll be having 3/4 of n, and that's plus, multiplying by n, again we have 2n squared plus n over, expanding the brackets at the bottom here, we'll be having 2n squared plus 2n. Now 3/4 of n minus 3/4 of n gives us 0. So we can say the limit as n approaches infinity of minus 4n squared plus n over 8n squared plus 4n plus, and here we have 2n squared plus n over 2n squared plus 2n, and this is equal to, or the same as, the limit as n approaches infinity. And here what I'll do is, for this algebraic fraction, I'll divide all the terms by n squared, which is the highest power term in the denominator. So it means I'll be having here minus of 4n squared divided by n squared is, we just get 4, and n over n squared gives us 1 over n, and it's over, and here we'll get 8, and 4n divided by n squared, we just get 4 over n, and that's plus, again here I'll divide by the term with the highest power, so n squared. So at the top we'll be having 2 plus, and here we'll be having 1 over n, and it's over, at the bottom dividing by n squared, we have 2, and here we'll be having 2 over n. So this is what we now have. Now we know that 1 over n has a limit of 0 as n approaches infinity. So here eventually we will get minus of, here that will be 4 plus 0, and at the bottom that will be 8 plus 0, and that's plus, here that will be 2 plus 0, and here that will be again 2 plus 0, and this simplifies to minus of 4 over 8, that's minus a half, and that's plus, here we get 2 over 2, which is 1, and minus half plus 1 gives us a half. So this is the final solution. Question 5. The lines L1 and L2 have equations r is equal to 3i plus 3k plus lambda I plus 4j plus 4k, and r is equal to 3i minus 5j minus 6k plus mu of 5j plus 6k, respectively. So on A, find the shortest distance between L1 and L2. Now, looking at the two equations, the first thing is you just have to check if the lines are going to be parallel to each other or not. And I think you know already that if the lines intersect, then the shortest distance between the two lines is 0. So here we will work this one out as if these two lines are skew. So there are many methods to work out the shortest distance between two lines, and the shorter one will be this one. So using this method, first of all, I would prefer to write these two equations in column vector form. So that will be r is equal to, that's 3, 0, 3 plus lambda, that's 1, 4, 4. So that's L1 here. And for L2, I'll write it as r is equal to 3 minus 5 minus 6, and that's plus mu of 0, 5, 6. So these are the two equations of the lines. So applying this method, it means that I'm going to start by looking for A1 minus A2. And for A1 minus A2, I'll be subtracting the position vector of points on the lines. So in this case, I'll be having 3, 0, 3, minus 3, minus 5, minus 6. And this is going to give me 3 minus 3, that's 0. 0 minus 5, that's 5. And 3 minus 6, that's 9. So that's A1 minus A2. And next, I'm going to find the cross product B1 and B2. So I'll be having 1, 4, 4, cross multiplying 0, 5, 6. So for the cross product here, I will close out the first two terms, and I'll have for this 2, 4 times 6, that's 24, minus 5 times 4, that's 20. Okay, so that's the I value. And minus, here I'll close out the two middle numbers. So 1 times 6, that's 6, minus 4 times 0, that's 0. And that's for J. And for K, I'll close the last two elements. So 1 times 5 is 5, minus 4 times 0, that's 0. And that's K. And what I'll get here is 4I minus 6J plus 5K. So I now have the cross product of B1 and B2. Next, I'm going to look for the modulus of B1 cross B2. And for this, I will simply say that's square root of 4 squared plus minus 6 squared plus 5 squared. And this is going to give me, that's 16 plus 36 plus 25. And we get from adding this 3, the square root of 77. So for D, I'll have the 1 over root 77 figured out. So that's 1 over root 77. And here under modulus, I'll have the dot product of A1 minus A2. So that's 059 dot B1 cross B2, which we got to be 4, minus 6, and 5 in column vector form like this. So let's simplify this. So the dot product here, we have 1 over root 77. We will have here 0 times 4, that's 0, plus 5 times minus 6, that's minus 30, and 9 times 5, that's 45. And we get 0 minus 30 plus 45 is 15. So this is 15 over root 77. And we can use our calculator to simplify it. So that's 15 over root 77. And we get 1.71. So that's equal to 1.71. And this here is the final answer. So that's it for part A. Let's scroll down to part B. So it goes, the plane pi contains L1 and is parallel to the vector I plus K. So on B, find the equation of pi, giving your answer in the form AX plus BY plus CZ is equal to D. So let's say this is the plane pi, and the line L1 lies on the plane, and we also have another vector I plus K, which is parallel to the plane. So we want to find the equation of the plane pi. Now we know that the equation of a plane is R dot N is equal to D. Now N is the normal, and in order for us to work out the normal of the plane, we would need at least 2 vectors on the plane. And these 2 vectors can be the direction vector of L1, which is 144. So we can have 144 here. and we cross that with another line on the plane, we can make use of the vector I plus k and kind of project it to the plane, so we can make use of it. So I plus k, that will be 1, 0, 1. So these two vectors are going to give us the normal. So let's do the cross product. So here I'll close the top elements, so that will be 4 times 1, that's 4, minus 4 times 0, that's 0, and that's I. And that's minus, I'll close the middle ones, so that's 1 times 1, which is 1, minus 4 times 1, which is 4, and that's j, and that's plus, closing the bottom ones, I'll have 1 times 0, and that's 0, minus 4 times 1, which is 4, and that's k. So we get the normal as 4i, and here plus 3j, and here minus 4k. So this is what we have. So we now have the normal to the plane. And now for D is a dot n, and a is any point on the plane. So here for D, I'll say a, any point on the plane. I'll use a point on L1. So a point on L1 is 303. So I'll use 303 for A. So 303, and that's dot. And N is what we got, 4, 3 minus 4, what we got here. So for the dot product, that's 3 times 4, that's 12. And 0 times 3, that's 0. And 3 times minus 4, that's minus 12. So this gives us 0. So we can now have the equation of the plane. So the equation of the plane will be r dot, and the normal, that's 4i plus 3j minus 4k. So this is what we have, and that's all equal to 0. Now we can also write this in Cartesian form as 4x plus 3y minus 4z equal to 0. So this is the final answer. Let's scroll down to part C. That's the last part of this question. Find the acute angle between L2 and pi. Now, a more convenient way to find the acute angle between a line and a plane is this formula here. So in this case, we know that L2 is the equation r is equal to 3 minus 5 minus 6 plus mu of 0.56. So let's write that down here. So the equation of L2, we're saying that's r is equal to 3 minus 5 minus 6 plus mu of 0.56. And the equation of pi, we got it just above. That's I'll write it in column vector form. So that's r dot 4, 3 minus 4 is equal to 0. So we want the acute angle between the line and the plane. So we will say sine theta is equal to, and that's b dot n. B is the direction vector. That's 0.56. And that's dot. That's 4, 3 minus 4. And it's over square root of 0 squared plus 5 squared plus 6 squared. We get root 61. And here, root of 4 squared plus 3 squared plus minus 4 squared, we get root 41. So at the top, the dot product is 0 times 4 plus 5 times 3, which is 15, plus 6 times minus 4, which is minus 24. We get 9. So it's 9 over root of 61 times 41. So this is all equal to sine theta. So we can find theta here as arcsine of this whole thing. So let's type that in. So that's shift sine, and we have 9 over the square root of 61 times 41. and it's giving us 10.4. So theta comes out as 10.4 degrees. And this is the final answer right here. Question number 6. Let A be equal to the matrix 2, 0, 1, 1. So on A, the transformation in the xy plane represented by A inverse transforms a triangle of area 30 square centimeters into a triangle of area D square centimeters. Find the value of D. So here the situation that we have is, they're saying that we've got a triangle. Actually, we have two triangles. So we have a triangle of area 30 square centimeters being transformed onto a triangle of area D square centimeters. So the transformation of the triangle of area 30 is being represented by the matrix A inverse. So they want us to find D. So here I'm going to use the fact that if A inverse is transforming the triangle of area 30 to triangle of area D, then it also means that the reverse will thus have matrix A as its operator. So that means that I'll be saying the determinant of A multiplied by triangle D should give us 30. And the determinant of A is 2 times 1 minus 1 times 0. So that's 2. So we have 2D is equal to 30. And dividing both sides by 2, we get D coming out as 15. Let's go on to part B. Prove by mathematical induction that for all positive integers n, a to the power n is equal to the matrix 2 to the power of n, 0, 2 to the n minus 1, and 1. So let's start with for n is equal to 1. Now for n is equal to 1, on the left hand side, we'll be having a to the power of 1. And we know that a to the power of 1, which is a, is 2010. So the left hand side has 2010 for n is equal to 1. Then how about the right hand side? For the right hand side, it means that we'll be having 2 to the power of 1 and 0. And here that will be 2 to the power of 1 minus 1 and 1 here. So this simplifies again to 2010, which is equal to left hand side. And so it's true for n is equal to 1. So next I will assume true for n is equal to k, which therefore means that I'll be having a to the power of k is equal to 2 to the power of k, 0, and 2 to the k minus 1, 1. So this is what we get. And now let's prove for n is equal to k plus 1. So for n is equal to k plus 1, we are substituting k plus 1 for n, so it becomes a to the power of k plus 1, which is the same as a to the power of k multiplying a to the power 1. So here, a to the k, we use the assumption, and on our assumption we've gotten 2 to the k of 0 and 2 to the k minus 1, and we're multiplying that by the matrix A, which is 2, 0, 1, 0. So let's multiply those two matrices. So here I'll say this is 2 to the power k times 2, we get 2 power k times 2, and that's plus 0 times 1, so that's 0. And then 2 to the power k times 0 plus 0 times 0, we get 0. Then 2 to the power k minus 1 times 2, we get 2 of 2 to the k minus 1, and that's plus 1 times 1, so it's plus 1. And then 2 to the power k minus 1 times 0 plus 1 times 0, we get 0. So we can simplify this now, and this is going to give us 2 to the power k times 2 to the power 1 is 2 to the power of k plus 1. Okay, the 0 remains here. And here 2 times 2 to the power k is 2 to the power of k plus 1. And 2 times minus 1 is minus 2. And minus 2 plus 1 is minus 1. And here we've got 0. Now, if you look at what we have, you can notice that if we put back n in place of k plus 1, it will come back to original formula here. So what we have now is the correct proof, and we're going to say, so it is also true for n is equal to k plus 1. And hence, by mathematical induction, it is also true for all positive integers. So that's the answer right here. Okay, let's move on to part C. The line y is equal to 2x is invariant under the transformation in the xy plane represented by a to the power of n times b, where b is equal to 1, 0, 33, 0. Find the value of n. So right here we've got this matrix here, which is transforming the line y is equal to 2x. So let's start by working out a to the power of n times b. So that's 2 to the power of n and 0, and 2 to the power of n minus 1 and 1. And that's pre-multiplying the matrix B. That's 1, 0 and 33, 0. So let's multiply the two matrices. So it means that we'll be getting 2 to the power of n times 1 plus 0 times 33, we get 2 to the power of n. Then 2 to the power of n times 0 plus 0 times 0, we get 0. Then 2 to the power of n minus 1 times 1 plus 1 times 33, we get 2 to the power of n minus 1 plus 33, which is plus 32. And 2 to the power n minus 1 times 0 plus 1 times 0, we get everything as 0 here. So this is the operator matrix here. Now, the line y is equal to 2x is invariant. So I'll need a general point on y is equal to 2x. That is, we can say when x is equal to k, what is y? So on y is equal to 2x, when x is equal to k, y will be 2k. And therefore, the general point is the point k and 2k. So if we transform any point on the line y is equal to 2x, it should show us that it's invariant. So what I'll do is I'll take the transforming matrix, which is 2 to the power of n, 0, and 2 to the power of n plus 32 and 0, and multiply this with k and 2k. And this is going to give me a new image like this. So let's work on this. So that's 2 to the power of n times k plus 0 times 2 to the power of k. So this gives us 2 to the power of n times k. And 2 to the power of n plus 32 times k plus 0 times 2k, we get k of 2 to the power of n plus 32. So this is all equal to x and y, the image. So here, x is coming out to be 2 to the power of n of k, and y is coming out to be k of 2 to the n plus 32 here. Now, we have these two equations, and we just want to form an equation of a line here. So we can say here for equation 1, k is equal to x over 2 to the power of n. And we substitute that into the second equation. Therefore, y comes out as x over 2 to the power of n of 2 to the power of n plus 32. So the new transformed equation is y is equal to 2 to the power of n plus 32 over 2 to the power of n all of x. That should be equal to y is equal to 2x, since according to the question, this line is invariant under the transformation. So we can safely say the line y is equal to 2x is equal to this line here. And this means that we can equate 2 to the power of n plus 32 over 2 to the power of n to 2 here. So multiplying both sides by 2 to the power of n, we get 2 to the power of n plus 32 is equal to, multiplying this times 2 to the power of n, we get 2 of 2 to the power of n. And if we subtract 2 to the power of n from both sides, we are going to get 32 here, and here we get 2 to the power of n. 32 is 2 to the power of 5, and that's equal to 2 to the power of n, and therefore we can conclude that n comes out as 5. So this here is the answer right here. Question number 7. The curve C1 has polar equation r is equal to theta cos theta for values of theta between 0 and half pi. So on A, the point on C1 furthest from the line theta is equal to half pi is denoted by P. Show that at P, 2 theta tan theta minus 1 is equal to 0, and verify that this equation is a root between 0.6 and 0.7. Now, whenever we are talking about a point furthest from the line theta is equal to half pi, you need to understand that we have to be considering the x equation, that's x is equal to r cos theta for our polar curve. In this case, x is equal to r, and r is theta cos theta, so that would be theta cos theta times cos theta, and this will give us theta cos squared theta. So for the point furthest from the vertical line, theta is equal to half pi, then we have to say dx by d theta should be equal to 0. So we can differentiate x with respect to theta, and doing so, it means we'll be getting cos squared theta times d theta of theta plus theta times d theta of cos squared theta. Okay, so this is differentiation of products that we are doing. So here, d theta of theta is 1, so we are left with cos squared theta. And here, differentiating cos squared theta, we get minus 2 cos theta sine theta. So this will be minus 2 theta cos theta sine theta. So this is what we get from differentiating this. And we're saying it's all supposed to be equal to 0, since we're talking about a stationary point furthest from the line. So for us to work this one out, we can factor out cos theta. So inside the bracket, we've got cos theta here. That's minus 2 theta sine theta, and that's equal to 0. So here it means either cos theta is going to be equal to 0, or cos theta minus 2 theta sine theta is equal to 0. So here I can manipulate this so that it can give me something like this. And how I can do that is I can divide both sides by cos theta. So I'll divide all the terms by cos theta. And if we do that, it means here we're going to get 1. And here sine theta over cos theta is tan. So we have 2 theta tan theta. And 0 divided by cos theta is 0. So dividing by minus 1, we have 2 theta tan theta minus 1 is equal to 0. So what we get here is what they wanted us to find. Let's go on to the other part of the question. Verify that this equation has a root between 0.6 and 0.7. So here I'll say let f of theta be equal to 2 theta tan theta minus 1. So here f of 0.6, we will have to calculate to see what we get from it, and also f of 0.7. So let's do that. So I'll take the calculator here, and we start with f of 0.6. Make sure that you're in radians. So 2 of 0.6 tan 0.6, and that's minus 1. And we get minus 0.179. So minus 0.179. And again, for 0.7, that's 2 of 0.7, and that's tan of 0.7 minus 1. And what we get is 0.179. So 0.179. So here we can see that there is a sign change, and hence it means that the root lies between 0.6 and 0.7. So that's how we do it. Let's move on to the next part of the question, part B. The curve C2 has polar equation r is equal to theta sine theta for values of theta between 0 and half pi. The curves C1 and C2 intersect at the pole denoted by O and at another point Q. So on B, find the polar coordinates of Q, giving you answers in exact form. So what we're seeing here in the question is that we've got two curves, C1 and C2, so we want to work out the point of intersection. So for C1, the equation is r is equal to theta cos theta. And for C2, the equation is r is equal to theta sine theta. So I'm equating this two. And if we do that, and I divide both sides by theta cos theta, then here I'll get 1. And here I'll get the theta cancelling out, and sine theta over cos theta is tan theta. So tan theta is equal to 1, and we know that theta here will come out as arctan 1, which is pi over 4. So we now have our value for theta. So now that we have the value of theta, we now need to work out the value of r. So here for r, we can use any one of the equations. R is equal to theta sine theta, so that will be pi over 4 sine of pi over 4, which we know to be pi over 4 of sine of pi over 4 is root 2 over 2, so that's pi root 2 over 8. So the polar coordinates will thus be in the form r theta, so r is pi root 2 over 8, and theta is pi over 4. So this is what we have as our answer. Let's move on to part C. On part C, they say, sketch C1 and C2 on the same diagram. Now, we have C1 with the equation r is equal to theta cos theta, and we have C2 with the equation r is equal to theta sine theta. Now, in order for us to sketch these two graphs, apparently they should be Ross curves. So I'll start with the Cartesian graphs of these two, where I will have on the vertical axis, I'll have r, and on the horizontal, I'll have theta. This is O here. Okay, and the range is from 0 to half pi, so it's just a small range. So I'll have half pi here, so that's pi over 2, which means here halfway I'll have pi over 4. So with a small table of values, I can see that when theta is equal to 0, theta cos theta also has a value of 0. So I'll have a point round about here. And when theta is equal to pi over 4, then theta cos theta, if you type it in, you have a value which is around about 0.56. So if this is 0.5, then 0.56 is slightly above it. And lastly, we have when theta is equal to pi over 2, then again theta cos theta is 0. So we will have the graph come out like this. And then for the graph theta sine theta, when theta is 0, then r comes out as 0. So we have a point around about here. And when theta is pi over 4, then r has a value of 0.56, the same as the one we got here. And then when theta is pi over 2, then r has a value 1.57. So if we have 1.5 around here, then 1.57 for pi over 2 will be a point just slightly above it. So the graph should come out more like this. So this is the other graph for C2. So we have this graph for C2 and this one for C1. So we now want to put this on a polar graph. So we'll be having it like this. So here this is theta is equal to 0 and this is theta is equal to pi over 2. And let's also have theta is equal to pi over 4. So here theta is equal to pi over 4. Now starting with C1, you can notice that as we approach pi over 4 from 0, the graph is increasing, r is increasing all the way up to 0.57. So we can represent it with this as we move towards pi over 4. And then as we move from pi over 4 to pi over 2, r decreases back to 0. So as we approach pi over 2, then it has to come back down. So this is the curve for C1. And then for C2, the one in black, as we move from 0 to pi over 4, r increases to 0.5. So we will also have that. And as we move from pi over 4 to pi over 2, it continues to increase all the way up to 1.57. So as we approach pi over 2, it's increasing to a value that is 1.57. So this is the other graph. So we now have the two curves. We have one for C1 and this one for C2. And that's how we do it for the two graphs. Let's move on to part D. On part D, they say find in terms of pi the area of the region bounded by the arc or Q of C1 and the arc or Q of C2. Okay, so let's go back to the graph. So the region that they want us to find is this shaded region here. That's the region bounded by C1 and C2 at Q. Q is this point here. So here we're going to use the range from theta is equal to 0 to theta is equal to pi over 4. And we're going to find the area under C1 for that region and subtract the area under C2 for that region. So we know the formula for area under a polar graph, which is the integral from alpha to beta of half r squared d theta. So in our case, we are saying for the shaded area, that will be the integral from, in this case, 0 to pi over 4 of the first graph is that of C1. And we know the equation of C1 is theta cos theta. So I'll have the half here and r squared will be theta cos theta all squared. So I'll have a square bracket here. And that's minus the graph of C2. So that will be theta sine theta squared. So I've just put it all in one. So this is what is going to help us to find the shaded area. So let's simplify this. So we're saying here that we have the half. I will put the half outside, and in integrating, that's from 0 to pi over 4, And here we have the theta squared. I'll factor it out again. So theta squared here, and inside the bracket I'll have cos squared theta minus sine squared theta, and that's d theta. Okay, so let's simplify again. So we have here, you need to understand that cos squared theta minus sine squared theta using the double angle formula is actually cos 2 theta. So it simplifies to this. Now what we have here can be integrated by parts. So we have to do integration by parts. So here I'm gonna say for the integral of theta squared cos 2 theta d theta, then let u be equal to theta squared and dv by d theta be equal to cos 2 theta. So du by d theta is 2 theta here, and v comes out as half sine 2 theta. So we can now do integration by parts for this. So it means that we'll be getting uv, that will be half of theta squared sine 2 theta, and that's minus the integral of v and du by d theta, which is integral of theta sine 2 theta d theta. But again here for this part we will also need to do integration by parts for the integral of theta sine 2 theta d theta. So again for the integral of theta sine 2 theta d theta, we can say let u be equal to theta and dv by d theta be equal to sine 2 theta. So here du d theta is 1 and v is minus 1 over 2 of cos 2 theta. So now we are going to integrate. So we're going to get uv, which is minus half theta cos 2 theta, and that's minus the integral of v and du by theta, which is minus, so I'll put a plus here, of half cos 2 theta, and that's d theta. So what we'll get is half theta cos 2 theta, and that's plus integrating half of cos 2 theta, we get a quarter of sine 2 theta plus c, though we will not need the constant of integration. So let's make use of this now to write down the integral that we're looking for, half of integral from 0 to pi over 4 of theta squared cos 2 theta d theta. So we are saying that half of the integral from 0 to pi over 4 of theta squared cos 2 theta d theta. So that's equal to a half, and that's off. And here we start with this part where we had half theta squared sine 2 theta when we did our first integration by parts. So that's half of theta squared sine 2 theta, and that's going to be minus the integral of theta sine 2 theta d theta, and we are done by parts for this, and we had obtained this. I left out a minus, so there has to be a minus this. So we are subtracting here. So that's if we subtract here, we get plus of half of theta cos 2 theta, and subtract here, that's minus a quarter sine 2 theta here, and we close, and the limits are from 0 to pi over 4. So now we are going to get, let me use some space here. So this is going to give us, putting the half inside, that will be a quarter of theta squared sine 2 theta plus a quarter theta cos 2 theta, and that's minus an eighth of sine 2 theta here, and pi over 4 and 0 the limits. So I'll substitute pi over 4 into this whole thing. It means we'll be having a quarter of pi over 4 squared of sine 2 theta, that's 2 of pi over 4, which is pi over 2, and that's plus a quarter of theta, which is pi over 4, and that's cos of 2 theta, which is pi over 2, and that's minus an eighth of sine of pi over 2. So this is what we have, and that's minus, and we substitute 0 into all this, and if we do that, we get minus of 1 over 8 of sine 0, which is 0. So we get nothing from here. So here, a quarter times pi over 4 squared, we get pi squared over 64, and sine of pi over 2 is 1. So this is fine. Then here, a quarter times pi over 4 times cos of pi over 2. This whole thing gives us 0 because cos of pi over 2 is 0. And then here we have minus an eighth of sine pi over 2. Sine pi over 2 is 1. So we get minus an eighth from this part. And this last part gives us 0. So eventually we'll be having our answer come out as pi squared over 64 minus an eighth. So this is what we get for the final answer. And this concludes the paper. Thank you for watching.